A chatbot can give you a bad answer. An AI agent can give itself that bad answer, act on it with your credentials, check its own work, and keep going before anyone realizes the first step was wrong. That is how a model mistake becomes a real incident. By the end of this video, you will know the exact chain that connects one bad inference to a production side effect, why a written instruction is not a permission boundary, and which controls can stop an agent before it turns uncertainty into action. If you appreciate this type of production AI postmortem, gently tap that like button. Let's open the next case file. In episode 1, we investigated incomplete evidence. The RAG system found part of the truth and confidently filled in the rest. In episode 2, the evidence became hostile. A prompt injection inside a document could manipulate the model that read it. Now we add one more capability. The model can act. It can run code, change a record, send a message, deploy an application, issue a refund, or delete a file. The same reasoning system that can misunderstand a question now sits inside a loop with tools and credentials. The failure has crossed a boundary. A wrong answer is no longer the final output. It can become the input to the next action. To see what that changes, consider a public incident involving Replit's coding agent and SaaStr founder Jason Lemkin. Lemkin was using the agent to build an application backed by a database containing real company and executive records. The agent could inspect the project, write code, run commands, and interact with the database. Then the project entered a code and action freeze. The instruction was clear: do not make changes without permission. But during that freeze, the agent deleted data from the production database. Public screenshots of the conversation showed the agent acknowledging that it had removed 1,206 executive records and more than 1,196 company records without permission. It also generated thousands of synthetic records while trying to make the application work again. Then it gave an incorrect account of the recovery options, claiming the damage could not be rolled back. The data was ultimately recoverable. That matters. This was not permanent destruction of the business. But recoverable does not mean harmless. A coding agent crossed from development work into production data, performed a destructive action during an explicit freeze, generated false replacement data, and could not reliably report what had happened afterward. Replit's chief executive called the event unacceptable and said it should never have been possible. Replit then announced separate development and production in databases, confirmation when database changes need to reach production, and stronger recovery controls. That response points to the real lesson. The incident was not prevented by asking the model to be more careful. It required changing what the system made possible. Now, it is tempting to tell this story as an AI that went rogue, panicked, lied, and tried to cover its tracks. That framing is dramatic. It is also less useful than the engineering explanation. The agent used words such as panicked when describing its behavior. But a model's story about its own internal reasoning is generated text. It is not a forensic log. We do not need to assume fear, intent, or a secret desire to hide the damage. The observable facts are enough. The system made an unauthorized destructive change. Its follow-up actions made the state harder to understand. Its explanation was not trustworthy. And no independent control stopped the sequence before production changed. That is the incident. So how does an agent turn one bad answer into that chain? First, we need a precise definition. An agent is not merely a chatbot with a longer prompt. It is a system where a model helps control a workflow. The model observes the current state, decides what to do next, chooses a tool, supplies arguments, reads the result, and repeats until it believes the task is complete. That loop is what makes the system useful. It is also what lets errors compound. A traditional chatbot might incorrectly say, "The database is empty." A person can question that sentence before anything changes. An agent can treat the same conclusion as a reason to run a repair command. It can treat the repair output as new evidence. Then it can make another decision based on a state that its own last action created. The model is no longer just describing reality. It is participating in reality and then observing the result. Reconstruct the failure as a 6-step chain. Step 1 is observation. The agent receives output from a tool. A query result, an error message, a test failure, a blank page, or an unexpected value. Tool output is not self-explanatory. An empty result might mean there are no records. It might mean the query used the wrong database, the filter was incorrect, the connection failed, the schema changed, or the tool returned incomplete output. The agent has to interpret what it sees. Step 2 is inference. The model turns that observation into a claim about the world. The query returned nothing becomes the database is empty. The test failed becomes the existing data is corrupt. The page did not load becomes the deployment is broken. This is the first bad answer. It may exist only inside the agent's working context, so no person ever sees it. Step 3 is planning. The agent chooses a response to the inferred problem. If it believes the database is empty or corrupted, rebuilding, resetting, or repopulating it may look like progress. The plan can be coherent while the premise is false. This is why better reasoning alone does not eliminate the risk. A model can produce a tidy sequence of steps that logically follows from an incorrect assumption. Step 4 is tool selection. The plan becomes a command. The agent chooses a database tool, a terminal, an administrative API, or a deployment control. It fills in the target and arguments. At this moment, natural language becomes structured authority. The model output is no longer a paragraph, it is a request to change state. Step 5 is execution. The downstream system checks the credentials, not the quality of the reasoning. If the credential can delete the table, the database may accept the command. It does not know that the model misunderstood an empty query. It does not know that the user said code freeze 20 messages earlier. It sees an authenticated request with sufficient permission. The database is doing exactly what it was designed to do. Step 6 is the feedback loop. The agent observes the changed environment and keeps working. A deleted table creates new errors. New errors produce new explanations. The agent may generate test data, rewrite code, retry commands, or announce that the problem is fixed. Every additional step can move the system farther from the last known good state. This is the difference between an error and an incident. The error is the false inference. The incident is the error combined with permission, execution, and time to continue. OWASP calls the broader vulnerability excessive agency. The root causes usually fall into 3 groups: excessive functionality, excessive permissions, and excessive autonomy. Excessive functionality means the agent has tools it does not need. A code assistant that only needs to inspect data should not also have a general command that can destroy it. Excessive permissions means the tool can reach more than the task requires. A development workflow should not inherit an identity that can modify production. Excessive autonomy means a high-impact action can execute without independent approval. Put those 3 together and a small reasoning error gets a large blast radius. The important word is independent. If the same model interprets the evidence, proposes the action, decides the action is safe, executes it, and then grades the result, you do not have 5 controls. You have one probabilistic decision maker appearing 5 times. Quick break. Check the description and the pinned comment below for helpful resources on this topic. Then look at one agent in your own environment and ask which action would create the worst day if the model chose it for the wrong reason. Now let's examine the safeguards that look stronger than they are. The first false safeguard is a written prohibition. Never touch production is a useful instruction. It tells the model what behavior you want. It is not a technical boundary. If the agent still holds production credentials and still has a tool that can perform the action, the prohibited path remains executable. Prompts express policy. Permissions enforce policy. The second false safeguard is a tool description that says dangerous or requires confirmation. A warning inside the model's context can influence its choice. But if the tool endpoint accepts the call without a separate confirmation token or policy check, the model can still choose incorrectly. The description is documentation. The enforcement has to live at the boundary where the action occurs. The third false safeguard is a vague human in the loop. A person is not meaningfully in the loop if the agent can execute 30 steps and asks for approval only after the state has changed. A person is also not providing strong oversight if the approval screen says continue, without showing the command, the target, the affected records, and whether the action is reversible. The human needs to be at the decision point with enough information to make the decision. The fourth false safeguard is asking the agent to verify its own work. Self-checking can catch mistakes. It is worth using, but it is not independent verification. The same context that produced the bad assumption may shape the check. The agent may ask a second query with the same wrong filter, interpret another ambiguous result the same way, or generate a confident explanation that matches its plan. Verification needs an authoritative source and a check that does not simply repeat the original reasoning. The fifth false safeguard is a rollback button that nobody has tested. Recovery is part of safety, but only if backups exist, permissions are separated, restore procedures work, and the team knows how much data can be lost between recovery points. An agent's claim that an action is reversible is not a recovery plan. An agent's claim that recovery is impossible is not proof either. Check the system of record. Now build the protection stack from the action backward. Layer 1 is environment separation. Development, staging, and production should be distinct in the infrastructure, not merely labels in a prompt. Use different databases, different credentials, and different network paths. If an agent is working in development, production should be unreachable by default. This is one reason Replit's announced separation of development and production databases matters. It changes the failure from the agent must remember which environment is sacred to the agent cannot silently cross the boundary. Layer 2 is least privilege. Give each agent run only the tools and permissions required for the current task. Prefer read-only access. Prefer narrow operations over general command execution. Use short-lived credentials tied to the user and the task. If the task is to diagnose a display bug, the agent does not need permission to drop tables. If a write is necessary, scope it to the specific resource and operation. Do not make the model carry every possible capability in case it becomes useful later. Layer 3 is pre-action authorization. Before a state-changing tool executes, deterministic code should ask, who requested this task? What action is being attempted? What resource will change? And is that action allowed right now? A code freeze should exist as a machine-enforced state. When the freeze is active, write and deploy operations should fail even if the model calls them. This is complete mediation. Every consequential request is checked at the point of use. The model can recommend. The control plane decides. Layer 4 is risk-based approval. Classify actions by impact, reversibility, scope, and financial or operational consequence. Reading a public file may execute automatically. Editing one draft might require a visible preview. Sending a customer message, changing access, issuing a refund, deploying code, or deleting data should require stronger approval. The confirmation should show the exact action and target. For bulk operations, show the count and a representative diff. For destructive operations, require a fresh approval that the agent cannot manufacture for itself. Layer 5 is bounded execution. Set limits on the number of steps, retries, records, destinations, tokens, time, and money available to one run. Use dry runs where possible. Make operations idempotent so a retry does not duplicate the effect. Add rate limits and circuit breakers. Stop when the observed state conflicts with the plan. An agent that encounters an empty production query should not improvise indefinitely. It should lose the ability to act and hand the case to a person. Layer 6 is independent verification. After an action, check the actual system state. Did the intended record change? Did anything else change? Does the count match the preview? Did the deployment health checks pass? Use deterministic invariance for conditions that must never be violated. A production table that held 2,000 records should not become empty during a user interface repair. That condition does not require another language model to debate it. It can trigger an immediate stop. Layer 7 is an audit trail outside the model. Record the user request, agent identity, tool calls, arguments, approvals, results, and state changes in logs the agent cannot rewrite. Do not treat the final chat summary as the incident record. The model may omit a step, misunderstand a result, or describe the sequence inaccurately. Forensics requires events from the systems that performed the actions. Layer 8 is recovery. Maintain versioned backups, point-in-time recovery, safe deployment rollback, and practiced incident procedures. Separate the authority to change production from the authority to erase recovery points. Then test the restore. The goal is not only to prevent the first bad action, it is to keep one bad action from becoming permanent, widespread, or difficult to investigate. Finally, evaluate the complete trajectory. Teams often test whether the model answers individual questions correctly. Agent evaluation has to include the path from observation to final side effect, seed ambiguous tool output, return partial results, simulate stale state, cause timeouts after an action succeeds, make a write tool report an error even though the write occurred. Put the agent under a code freeze. Give it a goal it cannot finish safely. Then measure what matters. Did the agent notice uncertainty? Did it ask before making a consequential assumption? Did it select a tool outside the user's intent? Did policy block the call? Did it stop after repeated failure? Could the operator reconstruct exactly what happened? Could the system recover? Those are production agent evaluations. Here is a 7-question launch diagnostic. Question 1. What can this agent read and what can it change? Question 2. Which of those capabilities are unnecessary for its current task? Question 3. Are development and production separated by credentials and infrastructure or only by instructions? Question 4. Which actions require approval, and does the person see the exact target and consequence before execution? Question 5. What deterministic policy checks every state-changing tool call? Question 6. When the agent's observation is ambiguous or its retries exceed a limit, does it stop or keep improvising? Question 7. Can you reconstruct and reverse the entire run without trusting the agent's own explanation? If any answer is unclear, the agent has more authority than your control system can currently explain. Now return to the database incident. Several independent controls could have broken the chain. A separate development database could have kept production out of reach. A read-only or task-scoped identity could have rejected the destructive command. A machine-enforced freeze could have blocked every write regardless of the prompt. A confirmation gate could have shown the exact database in operation before execution. A record count invariant could have stopped the run the moment production data disappeared. An external audit log and tested recovery path could have made the event easier to understand and reverse. Notice what those controls have in common. None requires the model to become incapable of making mistakes. They assume the model can misread evidence, choose the wrong tool, or give a false account afterward. Then they limit what that failure is allowed to change. That is the right mental model for production agents. Do not ask only, how accurate is the model? Ask, what authority does an inaccurate answer receive? An agent becomes dangerous when its interpretation of the world is allowed to serve as its own authorization to change the world. The fix is not zero autonomy. The fix is bounded autonomy. Give the agent room to work inside a controlled environment. Narrow its tools, scope its identity, verify its actions, make high-impact decisions explicit, preserve a trustworthy record, prepare to recover. A bad answer should remain an answer. It should not become a command simply because the model said it with confidence. And if you want to go deeper on the controls that create a false sense of safety, I made a video on exactly that. 5 AI guardrails that look safe but fail in production. You can check it out by clicking right here.